Today we are going to learn about building neural networks with backpropagation. We'll delve into the backpropagation algorithm, understand how it updates network weights, and learn to implement it effectively. By the end of this video, you'll gain the skills to minimize errors in neural networks using backpropagation.
Welcome to our session on building neural networks with backpropagation. In this video, we'll explore the backpropagation algorithm, a pivotal technique for training neural networks. Backpropagation is the process by which neural networks adjust their weights responsibly, minimizing error across the network. This approach has revolutionized the field of deep learning, enabling the development of sophisticated models that can learn complex patterns. Throughout this video, we will break down the components and processes that make backpropagation both powerful and efficient.
To understand backpropagation, we first need to grasp how error is calculated in a neural network. The error, or loss, measures how far off a model's predictions are from the actual outcomes. Common loss functions include mean-squared error for regression tasks and cross-entropy loss for classification tasks. Once we have the error, the next step is to minimize it, which is where gradient descent comes in. This optimization algorithm iteratively adjusts the model's weights to reduce the error. It does so by computing the gradient of the loss function, which indicates the direction of steepest descent. By moving in the opposite direction, the gradient descent algorithm helps to minimize the error effectively. This process is foundational to backpropagation, as it relies on gradient descent to fine-tune the weights of a neural network iteratively.
The chain rule is a fundamental concept from calculus that plays a crucial role in backpropagation. It allows us to compute the derivative of composite functions, which is essential when dealing with the layered structure of neural networks. In the context of backpropagation, the chain rule helps us calculate the gradient of the loss function with respect to each weight in the network. By efficiently propagating these gradients backward through the network's layers, we can determine how each weight contributes to the error. This process enables the model to make precise adjustments to the weights, improving its performance. Understanding the chain rule is vital for grasping how backpropagation works, especially in deep networks where multiple layers are involved. In backpropagation, once gradients are computed using the chain rule, the next step is to update the weights of the neural network. This is where the learning rate comes into play. The learning rate is a hyperparameter that determines the size of the steps taken during the optimization process. If the learning rate is too high, the model might overshoot the optimal solution, causing it to diverge. Conversely, a very low learning rate can lead to slow convergence, making the training process inefficient. Striking the right balance is crucial, and often, practitioners use techniques like learning rate schedules or adaptive learning rates to optimize this process. By fine-tuning the learning rate, we ensure that the model converges effectively, achieving better performance. Training neural networks with backpropagation can be challenging, and several pitfalls can affect the model's performance. One common issue is overfitting, where the model performs well on training data but poorly on unseen data. To combat this, techniques like dropout, L1 and L2 regularization, and data augmentation are employed. Another challenge is the vanishing gradient problem, particularly in deep networks. This occurs when gradients become too small, hindering effective weight updates. Techniques such as batch normalization and residual networks can help alleviate this issue. Additionally, ensuring data is normalized can significantly impact training efficiency and model performance. By being aware of these pitfalls and implementing effective strategies, practitioners can enhance the robustness and accuracy of their models. Visualizing the learning process of a neural network can provide valuable insights into its behavior and performance. Tools like TensorBoard and Matplotlib can be used to track metrics such as loss and accuracy over time. By visualizing weight updates and observing how the model converges, practitioners can diagnose potential issues and make informed adjustments. Visualization helps in understanding how different hyperparameters, such as learning rate and batch size, impact the training process. It also offers a way to analyze the effectiveness of various optimization techniques and regularization methods. Through visualization, we can gain a deeper understanding of the network's learning dynamics, leading to more efficient and effective training.
Now that we've explored the theory behind backpropagation, it's time to implement it in Python. Several libraries, such as TensorFlow and PyTorch, offer built-in support for backpropagation, simplifying the process. However, understanding the underlying mechanics is crucial, so we'll start with a manual implementation. First, we'll define a simple neural network with an input layer, one hidden layer, and an output layer. We'll then initialize the weights and biases randomly. Next, we'll write functions to perform forward propagation, calculate the error using a loss function, and apply backpropagation to update the weights. Once the implementation is complete, we'll test it on a small dataset to ensure it works correctly. Finally, we'll discuss ways to optimize the code for better performance, such as using vectorized operations and leveraging GPU acceleration.
Backpropagation has been instrumental in advancing various fields by enabling the development of powerful neural networks. Let's explore some case studies of successful implementations. In the healthcare industry, backpropagation-powered models have improved diagnostic accuracy by analyzing medical images and predicting patient outcomes. In finance, neural networks have been used for fraud detection and algorithmic trading, enhancing security and efficiency. The automotive industry has leveraged backpropagation in autonomous vehicles to process sensor data and make real-time decisions. These examples highlight the versatility and impact of backpropagation across different domains. By examining these case studies, we can learn valuable lessons about the challenges faced and the innovative solutions that have been developed. The future of backpropagation holds promise for even more groundbreaking applications as technology continues to evolve.
As we conclude this video on building neural networks with backpropagation, let's recap what we've learned. We've explored the core concepts of backpropagation, from error calculation and gradient descent to the chain rule and weight updates. We've also discussed common training pitfalls and strategies to overcome them, as well as the importance of visualization in understanding the learning process. With a practical implementation in Python and insights from real-world case studies, you're now equipped with the knowledge to build and train neural networks effectively. We encourage you to continue exploring this exciting field and experiment with backpropagation in your projects. Thank you for joining us, and happy learning.